Okay. Okay. So here I gotta let's see. How do I do this? I go here and I go. Is that it? Yeah, that's it. Okay, perfect. Okay, so the limit of f of x as x approaches, which one are we interested in? Obviously, 0 is clearly a 0 of the denominator, isn't it? Right? Agreed? Okay. So, okay, well, first of all, let's do this one. Let's do part A first. What's the limit as x approaches infinity? If I were to, the bottom's not written as a polynomial in standard form, but I could write it that way, right? I could write f of x as x squared minus 4 over x squared minus 2x, right? So all I have to do is look at the ratio of the leading terms, and what do I get? 1. Agreed? Okay, so this guy, so here. Okay, because it's wanting horizontal asymptote. Was that the only issue? Yeah. Mm-hmm. It is, right? Because we're taking limits at infinity. You are. The limit, so the limit of f of x. When you're doing horizontal asymptotes, yeah. If you're right, if you're evaluating a limit, just means taking a limit, right? So if we're taking a limit at infinity, what's this telling us? The limit of that is equal to the limit of the ratio of the leading terms, as long as I'm approaching the infinities, right? That's when we can do that. So x squared over x squared is 1. So I just get 1 for both those. Okay, so that one's knocked out. That's one. That's one. Check answer. Boom. Okay. Part B. Well, so what are the horizontal asymptotes? Yeah. So it's only got one horizontal asymptote, so it goes there. Okay, vertical asymptotes. Where are they going to be? Or how many are we going to have? So here's where we've got to do this stuff, right? If I factor the top and the bottom, the limit of this function is equal to the limit of x minus 2 over x plus 2 or times x over x minus 2. Okay, well, what's going to happen there? What are the interesting limits? I guess we want to take a limit as x approaches 2 probably, right? What are the zeros? I'm not being very articulate here. What are the zeros of the denominator? 0 and 2. So those are my candidates, right? Well, let's write that down. Okay, so that's first thing. If we're trying to find vertical asymptotes, they could only occur at zeros of the denominator, okay? Whoops. Oh, I want to do that. I want to do that. I'm struggling here. Zero and 2, okay? Are any of those unique zeros of the denominator? 0 is, right? So right away, we know one of them, we definitely have a vertical asymptote at 0. What about 2? We don't know, because 2 is a shared 0 of the top and the bottom, right? So we have to do more work. We'd have to take the limit as x approaches 2. Okay, well, what would we do here? We would cancel, we'd factor and cancel, right? And so we end up with the limit of x plus 2 over x as x approaches 2, which is just 2, right? 4 over 2. Okay, so then is x equals 2 a vertical asymptote? It's not, right? Because when we took the limit, it was indeterminate, right? When we tried to take the limit, it was indeterminate, which means we don't know. More work is required. When we did more work, we found out that the limit is finite. It's 2, okay? If we had gotten an answer where when we did more work, we ended up with a 0 on the bottom and a number on the top, then it would have been a vertical asymptote, right? There were two things that could have happened. When we initially tried this, when we took the limit as x approaches 2, we got the form 0 over 0, which is indeterminate, right? So we don't know. Either thing could be happening. Either it could be a hole or it could be a vertical asymptote. We don't know yet. When we resolved the indeterminacy, we found out that it's a hole because we end up getting an actual limit, which means the ant anticipates stepping on the y value 2. Does he get there? Well, no, because 2 is excluded from our domain. The function's not defined there, so there's a hole in the function there. Okay, does that make sense? Right, you see how we approach that? This goes back, okay, what might be helpful, when I'm done with this, remind me to go back to the lecture where we did a problem like this. I want to show you a slide in there that I think will be helpful. Okay, but it's I'm gonna wait till I'm done with this because it's hard to jump back and forth like this when I'm in this mode where I'm annotating on the desktop. Okay, so then what's my only vertical asymptote? 0. Okay, because 0, okay, right, does that make sense? So we end up with, has one vertical asymptote at x equals 0. Okay, now they want to know, okay, they want to know what's going to happen as we approach 0 from the left and the right. Okay, we can do that too. Okay, so we got, when we factored this thing, as we approached 0, so let's go back up here and let's take a limit as x approaches 0. The limit of x minus 2, and we could even just leave it like that. The limit of my function, x squared minus 4 over x times x minus 2, as x approaches 0 from the left, is going to be what? On the top, we're going to get negative 4, right? On the bottom, we're going to get, what's that going to turn into? 0 minus, right? As I approach 0 from the left, x becomes a small negative number. So that's going to look like 0 minus times, if I plug 0 in there, I get negative 2. So what's my answer going to be? I know I've got some kind of infinity because I've got a 0 on the bottom but not the top. What's the flavor going to be? Positive or negative? Negative, because look, I've got an odd number of negatives that are being multiplied and divided. Okay, what if we took the limit of x squared minus 4 as x approaches 0 from the right? What am I going to get? Everything's going to be the same except that term's going to change, right? I'm still going to get -4 on the top, but this is going to become a 0 plus. 0 minus 2 is still a -2, so now I get a positive infinity. Make sense? Okay. So then, where were we here? So we were here, weren't we? 0. As x approaches a, which is 0 from the left, we had negative infinity. As x approached 0 from the right, we had positive infinity. Okay, make sense? And then that's it. Okay, does that make sense? I'm going to put this up. I'm recording this. I'm going to put this up as a separate video, so it'll be short. If you need, this is important stuff, and there's a lot of moving parts. If you need to go back and in the, where you can sit in the quiet and pause and think and stuff, hit this one again. Okay, this one might not be a bad one to hit. Let's look at one more thing. Any questions on that before I go any further? Okay. All right, so now let's do this. Let me get rid of those guys and let me get out of there. And I want to pull up that old flip chart. And what was it? It was, where did that one pop up? I'm just trying to remember. Oh, where was that? I'm just going to scan through a couple real quick and see which one it was. Right here. This is it. Okay, look at this. This is the slide we need to see. Okay, how do you know whether a function that is undefined at x equals c, but is defined at all other values in the neighborhood of c, has a hole or an asymptote? So what's that mean? That means we have c is a 0 of the denominator, right? We often assume that if the limit as x approaches c is indeterminate, that it must be a hole. Not true, right? If we get 0 on the bottom but not on the top, we automatically know it's a vertical asymptote. If it's indeterminate, it is truly indeterminate. We don't know if it's a vertical asymptote or a hole. So what's our strategy? After removing the indeterminacy, so we're going to typically, if we're starting with a rational function, we're going to cancel the factors that are causing the 0 over 0 to happen. After removing the indeterminacy, if direct substitution gives us an answer, then if the limit gives us a numerical answer, some number other than infinities, then I know it's a hole because the ant is approaching a specific value. So that means a hole. After removing the indeterminacy, if we end up, when we directly substitute, getting something of the form a number divided by 0, okay, then it turns out that indeterminacy really was masking a vertical asymptote. And here's the example we looked at in class, was one very similar to the one we just did, right? Look at this function here, this blue one. If I try to take the limit as x approaches 2, I get 0 over 0, right? Indeterminate. When I resolve the indeterminacy by factoring the top and factoring the bottom and canceling factors, I'm left with the limit of x minus 2 as x approaches 2, which is 0. I got an answer, so it's a hole. There's a hole at y equals 0 and x equals 2 because that's the value we were approaching. The ant anticipates stepping on that point, but it doesn't exist because the function's not defined at 2. Give me thumbs on that. Okay. Look at this one, similar. Again, if I try to evaluate this limit directly, I'm going to get 0 over 0. If I evaluate the limit at 2, right? So I've got to factor and cancel. Well, I factor the denominator, I cancel a factor of x minus 2. Now I'm left with 1 over x minus 2. When I evaluate that limit, I get 1 over 0, vertical asymptote. Okay? Make sense? Okay. Okay, that's where I wanted to go. Any other questions? Homework questions. Number 9, sure. Okay, so let me go back. Okay. Okay, we'll just look at this one with the answers in there and see if we can figure this out. So evaluate the limit as x approaches infinity and as x approaches negative infinity. Well, what's the answer going to be? Look at that one. That's one of our rules. If I've got a rational function and I'm taking the limits at infinity, what's the rule going to be in this case? 0. How come? You're right. Okay, because the bottom is a higher order polynomial than the top. And let's go back again and look at the notes on that. Let's see, limits at infinity, right there, okay? It's just that stuff, right? Okay, all we're looking at is this. Guidelines for finding limits at positive or negative infinity. If the degree of the numerator is less than the degree of the denominator, you automatically know that the limit's going to equal 0, so you have a horizontal asymptote at y equals 0. If the degree of the polynomials in the top and bottom are equal, then we take the ratio of the leading coefficients, right? And we also get a horizontal asymptote, okay? If the top is a larger degree than the bottom, then there is no horizontal asymptote, okay? So then what about this guy? You can remember those rules, or what I would do is not even use the stupid rules. I would just say, not stupid, they're great rules, but the limit of a rational function as x approaches the infinities, a limit of a rational function is equal to the limit of the ratio of the leading terms only, right? Because they dominate the behavior. So this is equal to the limit of 5x to the 5th over x to the 6th as x approaches plus or minus infinity. And if I cancel factors, if I divide top and bottom by x to the 5th, don't I just get the limit of 5 over x as x approaches plus or minus infinity, right? What's that going to do? If the bottom explodes and the top is stuck at 5, isn't that just 0? Right? Everybody agree? Think about the behavior of a fraction. If the bottom gets huge and the top doesn't, the fraction goes to 0. Right? Make sense? Okay. So then on this one, does it make sense that, does it make sense that we get 0, right? As x approaches infinity, it's 0. As x approaches negative infinity, it's 0. And so we get a shared asymptote at 0. There's only one. Okay, give me thumbs. Well, they they are connected, right? What does an asymptote mean? A horizontal asymptote is asking about the behavior of the function where? Not for small values of x. It could do all kinds of crazy things. Horizontal asymptotes ask about the behavior where on the function? Way out to the right or left at the ends of the function or the tails of the function, right? And so how would we figure out what that is? If we want to know what the value of, if there's a horizontal asymptote, the limit of the function as x approaches positive infinity or negative infinity would have to be some constant value that the function is approaching. Okay? Does that make sense? Okay, think what that would look like. Here, let's draw a picture. just to remind you. So like if we're doing one like this, so if I've got some function, if the limit of f of x as x approaches plus or minus infinity, let's just say we get the answer, it's equal to 2. Could be 0, could be -3, whatever. What's that graph going to look like? That means that y is going to approach the value 2 way out at the ends of this function. So there's my horizontal asymptote. In here, the function could be doing all kinds of crazy things, right? It might be doing something like, whoops. It might be doing all kinds of crazy stuff. But as we go very far out to the edges, it's going to start to cling more and more closely to that horizontal line. Okay? Does that make sense? So do you see the connection there? A horizontal asymptote is just the line that the function approaches at the ends of the function. It's end behavior. How do we determine end behavior? Well, that's taking a limit as x is approaching the infinities. You can't plug infinity in because it's not a number, but we could take a limit as x approaches infinity. Okay? Does that help? Yay or nay? A little bit. Okay. And I don't expect you to say, yeah, I got it now, because it rarely works that way in math. When I would go in and see my advisors in college, they would show me some stuff and I would think, okay, I kind of see a roadmap there, but I had to go home and sit down and look at that stuff for a while before the light came on. I said, oh, okay, now I got it. Now it makes sense. I connected those things in my brain and then it was fine. So you might have to do that. Yeah. Practice 6? Yeah, you bet. Okay. Okay. How do I do that? Do I go there? Yes, I do. Okay. All right, practice 6. Cancel. That was practice 5 we were looking at, right? Yeah. Okay. End behavior. Okay, which one are we looking at? Number 3. Okay. Okay, good. I'm just going to take a picture of this one so I can just write. I think that'd be easier. Is there anything else on that? Yeah. Okay. Okay, what about this guy? So here we got this function. We want to evaluate the limit of this function at the infinities. Okay, so if we try to, right now, it doesn't help us much because we've got this weird square root up there, right? If I try to, I can't really plug infinities in anyway, right? How could I deal with this though? The limit, let's just take the first example. Let's take positive infinity. Okay. The limit of the square root of 4x squared plus 3x plus 18 minus 5 over x minus 1 as x approaches infinity looks very complicated. Could I trade that for a simpler limit? Right? As x is approaching infinity, is there a dominant term on the top and the bottom that's going to be the only one that matters? the leading term, right? So it's going to be really, there's a polynomial inside the square root, but if we focus on the polynomial that's inside the square root, when x gets huge, the first term is going to dominate the behavior. That's the only one we need to consider, right? On the bottom, the leading term is just going to be x. That's going to be the term that dominates the behavior as x approaches infinity. So we could trade this then for a much simpler limit. It's going to be the limit of the square root of 4x squared divided by x. Right? Everybody see that? And how do we get that? Well, really, we're just looking at this part. That's the part that's going to dominate, right? Okay, what is, let's simplify, the square root of 4x squared? What does that become? 2. Okay, yeah, so let's use our properties of radicals here. The square root of a times b is equal to the square root of a times the square root of b. So I can break this into the square root of 4, which is 2, right? What's the square root of x squared? It's not x, it's, what was it? Absolute value of x, exactly. There's the key connection, right? That's the part we got to remember. We got to remember that the square root of x squared is equal to the absolute value of x. That makes this thing much, much simpler, right? Over x, okay? So as x approaches infinity, x is a positive number then, right? What is the square root of x equal to if x is approaching a positive number? What's the square root of 7? I mean, sorry, I'm saying square root. I meant absolute value. I wish I could just, I wish I could rewind that. Okay, you see, I said square root several times there. I meant absolute value. Rewind that about 30 seconds. What is the absolute value of x equal to when x is approaching a positive number? What's the absolute value of 7? 7. What's the absolute value of a trillion? A trillion, right? As x approaches infinity, it doesn't matter. It's a positive value. So the absolute value of x is just equal to what? X, right? Remember that? And we talked about that the other day by thinking of it as a piecewise function. The absolute value of x is always equal to x when x is positive, right? It equals negative x when x is negative, right? What's the absolute value of negative 7? 7. How'd you get to 7? You multiplied negative 7 by negative 1, right? You always multiply the input value by negative 1 if you're inputting a negative number into an absolute value, right? Okay, so then what do we get here? So this becomes the limit of 2x over x as x approaches infinity, which is what? Yeah, look at that. The x's cancel now, don't they? Right? So we end up getting 2. Agreed? Okay. So then while we're at it, let's do the other one. Let's do the negative one. Okay, we already got to here, didn't we? Right? The limit of f, we'll call that whole thing f of x as x approaches negative infinity is just going to be the limit of 2 times the absolute value of x over x as x approaches negative infinity. What's the top going to become when we're approaching a negative number? What do I replace the absolute value of x with if I'm approaching a negative value? What's it equal to? Okay, again, what's the absolute value of negative 10? 10, which is the same thing as negative 10, right? So what's the absolute value of x equal to if x is a negative value? negative x, right? Because I've got to make it positive, right? This is negative. So that means I can replace that absolute value of x, whoops, with, oh my goodness, there we go, with negative x, right? Anybody see that? Okay, how come? That's why. An absolute value function is equal to the opposite of x whenever x is negative. Okay, we go back to that a lot. What's on the bottom? X. Okay, well that's equal to the limit of negative 2x over x as x approaches negative infinity. Well, the x's cancel. What do I get? Negative 2. Okay, that really shouldn't surprise us because let's focus on this thing for a second. Let's think about this in a different way that's completely consistent. Okay, so what is that graph going to look like? If I graph that function, if I take the function f of x equals 2 times absolute value of x over x, what was that graph? We looked at it the other day. If I graph the absolute value of x over x, remember that was that step function, right? Yeah, didn't that just look like this? That just looked like that function, right? Everybody agree? What happens to a function if I multiply it by 2? Stretches it by 2, right? So multiplying by 2 is going to change that into the green function when I multiply by 2. That's what we got, isn't it? The limit at infinity was positive 2. The limit at negative infinity was negative 2. Okay? Make sense? Okay. All right, anything else? Okay. Okay. Okay, yeah. So this, I get this one because this one I just kind of left up to you guys. This is, we need to do a little review of exponential functions is all we need to do here. And this is really kind of cool because I'm sure you have for many years wondered about the behavior of squirrel populations, right? Okay, so then we got to define a couple terms. Yeah, I kind of left you guys to contemplate this one. We haven't talked about this yet. I'll do that every once in a while. What do you think a steady state is going to mean in a population? You guys are taking biology, taking advanced biology, right? Do you know what steady state is? You guys didn't talk about steady state ever? Okay, who's in AP Bio? You guys have to have talked about steady state, right? No? What do you think it is? What do you think a steady state is in a population? Yeah, okay, steady state would mean where the population is steady. It stays at the same level forever, okay? Population, if everything is in perfect harmony, a population will just stay the same size, okay? So we want to know, does a steady state exist in this population? Well, how would we know? This is the growth model for our squirrel population. If we want to know what's going to happen as time progresses for a long time, what value of t are we going to be plugging in? Infinity, right? But we can't plug infinity in. Instead, we have to take a limit. Infinity is not a number we can just plug in, right? So we have to take limits as we approach infinity. So that's really all we're doing here. To figure this out, we're going to take a limit of our population function okay, as t approaches positive infinity. We're not going to go back in time with these squirrels. We're just going to go forward in time, right? If we try to evaluate this thing directly, we can just power through this. The part that we're interested in is this part right here. E to the negative 0.09t. What does a negative exponent mean? Like, what is e to the, hey, let's not even use e. What is a to the negative n equal to? 1 over a to the n, right? Remember talking about this a couple years ago? What did we always say? A negative exponent in one part of a fraction is a positive exponent in the other part of the fraction, right? They're equivalent. So we could rewrite this as the limit of 1800 over 2 plus, that goes to the bottom, so I get 9 over e to the positive 0.09t. Agreed? As x, or as t, approaches infinity. That's a plus sign, not a t. Okay, so if we let t go to infinity, what is this quantity? What's going to happen with that quantity? E to a huge value is going to do what? What's the limit of e to the positive 0.09t as t approaches infinity? E is a number bigger than 1, 2.7182. If I take some number pushing 3 to an infinitely large exponent, what's the outcome going to be? Infinitely large, right? Think about like e, let's just make it 3. 3 to the 10 is enormous, right? 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, 3 to the 5th is 243. It's grown pretty big, right? If we take e to a huge exponent, I'm clearly getting infinity for an answer, right? Okay, well, what's 9 divided by a huge number, a number approaching infinity? 0, right? I get a big number in the bottom of this fraction and 9 on the top. So the behavior is going to be that this term right here, wrong color, let's do this. This whole term right here, this whole thing is going to approach 0 then, that fraction, right? Well, if that fraction approaches 0, don't we just get the answer 1800 over 2, which is 900? What's that tell us? What's the population, the squirrel population, going to approach as time moves far into the future? 900, and it's going to stay there. It's a horizontal asymptote. So does it have a steady state? Yeah, it does. Okay, make sense? Okay, all right. That was probably time well spent. You guys, I assume you needed a day to catch your breath on that stuff. I'll put the notes up, I'll put the video up, and we'll come back to this other stuff later.